this part of dynamic, we will be dealing with curvilinear motions that is based on normal and tangential components. The normal components is when the components, the accelerations or the velocity of the components is pointing towards the center of rotation. And the tangential components always taken as the tangential components that is along the tangential line, which is touching the curvature of the path. So example, this is the first example. Then this will be the second example. You can take a look at the example of the application of this section. So velocity V can be analyzed using N and T, where N is referring to the normal component and T as the tangential component. The magnitude of the velocity is changing and also the acceleration as well. So this is another example referring to a roller coaster which is moving in a curved path. Okay, so in this section here, the normal and tangential component, the tangential refers to T and the normal component refers to N. So that is the N and the T coordinates. In the N and T coordinate system, the origin is located, remember here, the origin is located on the particle itself. Okay, and the origin will move with respect to the movement of the particle. So T-axis is being tangent to the path of the curve, and then N-axis is taken as the perpendicular axis, which is always moving towards the center of curvature or the center of motion. So the positive N and T directions are defined as the unit vectors of UN and UT respectively. So these are the unit vectors for the normal and the tangential component, with the subscript N refers to the normal component, with the subscript T refers to the tangential component in the diagram besides. Okay, so the center of curvature always lies on the concave side of the curve, and the radius of curvature is always defined as a symbol of rho, or you can use it as radius r. So either you can use it as rho or r. The position of the particle at any instant is defined by the distance of s. So along the curve from a fixed reference point. Usually the s is referring to the arc of motion. Velocity in the N and T component systems. So the velocity vector is always tangent to the path of motion in the T direction for the tangential component. The magnitude can be determined by the time derivative of the path function. So let's say, for example, in the question, if they have given us v in terms of s, let's say v is equal to 6s. So when you differentiate s with respect to t, so you got the s dot, so that will give you a 6. Example. Here v defines as the magnitude of the velocity, which is the speed, and the ut is referring to the direction actually. So you have the magnitude and the direction. The acceleration component, the time rate of change of velocity. So you can take acceleration here as dv over dt. Okay, so when you differentiate that, you will have the v dot with the vector, with the unit vector in the tangential component of ut, and the v with the tangential component vector of u. So here v dot represents the change in magnitude. Now, so to calculate the acceleration or the magnitude of the acceleration, or the acceleration vector, sorry, this is acceleration vector. Whenever you see the ut and the un, whenever the question asks you to write it in vector form, so you have to include the ut and the un, and with the v dot and the v square over rho, where v dot is the tangential acceleration actually, and v square over rho is actually the centripetal acceleration or the normal acceleration. Bear in mind that formula. So there are two components of acceleration. One is the tangential and the other one is the normal. So same as for the velocity. So the tangential component A with the subscript of t is actually equals to v dot, or you can take the derivative of the velocity. The normal or the centripetal component, so it is known as centripetal because it is always directed towards the center of rotation. Okay, it's always directed towards the center of curvature of the curve. So an is always given as, it can be found by using v square over rho. Rho is where the rho is the radius. So the magnitude, so you can take the square root of at squared plus the an squared. Now, for special cases of motion, let's say the radius becomes infinity. That means if it is a horizontal line, then there should be no normal acceleration. So you can say that v squared over rho or an is equals to 0. So the magnitude of accelerations is only depending on the tangential acceleration, because the normal acceleration has already become 0 since it is moving in a straight line or a horizontal line. So that is only the tangential component, and which can be found by taking the time rate of change of magnitude of the velocity. 2. The particle moves along a curve, but it is at constant speed. If it is at constant speed, then the tangential acceleration would be equals to 0. But then the normal acceleration is still equals to v squared over radius rho. The normal component represents the time rate of change of the directions of velocity. So you have to do a lot of differentiation here. The third one, if the tangential component of acceleration is constant, then the tangential component, the tangential acceleration we can use equation as what we have done earlier, the first, second, and the third acceleration. Now, the first referring to the position or the displacement, the second one refers to the initial velocity and the final velocity, and the third one is the initial final velocity with the change in position. Remember these three formulas that we have done earlier. Okay, as before, S0 and V0 are the initial positions and velocity. That means the initial position and the initial velocity of the particle when the time is equals to 0. That means at the starting point. So for the particle which moves along a path is expressed by the path functions. So the radius of curvature, that is the r, at any point on the path can be calculated by the formula given below. Okay, so you can use this formula here, provided they have given you an equation y is equals to something in respect to x. So we can find dy dx and the d squared y over dx squared. If it is three-dimensional, now what we have done here, wherever you have normal and tangential component only, that is two-dimensional. So if it is three-dimensional, then you have to refer to another axis, that is b. Okay, so if a particle moves along a space curve and the n and t axes are defined as before, that is that is a single plane, that means with the axis of n and t, which is 2D. Now at any point the t-axis is being tangent to the path of the motion, and the n-axis is always towards the center of curvature. The plane containing n and t-axis is called the oscillating plane. That is one plane only. Okay, so if you have the third axis that appeared, so that will be called as the binomial axis. So that is 3D now. Now the binomial unit vector, okay, so unit vector is always defined as the symbol of u. So in which directions, then you will have the subscript of either t or n or b or x or y. It depends on whether it's xy or it is t and n in this case, and b for the third axis. So it's directed perpendicular to the oscillating plane. So the first plane that we have is at n and t. So b is always being perpendicular to the oscillating plane, and its sense is defined by the cross product of the ut and the un. There's no motion, there's no velocity or acceleration in the binomial direction. If there's no motion in the z or the b direction, then there will be no velocity and acceleration in that direction. Now here there's a working example. As I have shown, a car travels along a road with a speed of v equals to 2s. From here you can take the partial derivative of v with respect to t, okay, or the dv over ds. Okay, so where s is in meters and have given us the radius of rotation or the curvature. The radius of the center of curvature is 50 meter. So the magnitudes of the car that is given in the diagram, okay, s is equals to 10 meter. So if s is equals to 10 meter, okay, so the magnitude of the car acceleration s equals to 10 meter. Now first thing, you have to calculate the velocity when s is equals to 10 using the power function of v to s. Now then calculate the tangential and the normal components of acceleration and then the magnitude of acceleration vector. So the first one, look at the solution here, the velocity vector. So whenever you say a vector is always represented, as you can see, with the ut or un and so on, where the magnitude is given by v is equals to 2s. So s is equals to 10 meter. So from here we can find out the velocity by substituting s, which is equals to 10. So you get the velocity is 20 meter per second. Then the acceleration formula that you have in vector form, okay, in vector form. So that is in vector form, so you have a v dot and your v square over rho. So you have to find your v dot. So since a tangential acceleration is equals to v dot, so therefore you have to differentiate the v with respect to t. But then we cannot differentiate v with respect to t directly. So you have to use a little bit of trick by taking dv over ds times ds over dt, so that you have v equals to dv over ds. So that means you differentiate v with respect to s, which v is equals to 2s, so you get a 2 from there. Okay, so you have 2v in this case, and we know that initially we have calculated that the v is 20 meters per second. So we just substitute the v, which is equal to 20 meters per second. So we get our tangential acceleration as 40 meters per second squared. So the normal component, this is for the normal component, so that is v squared over rho. And the magnitude, you can take the square root of at squared and the an squared. So you have 40.8 meters per second squared. That's for the acceleration. Now, second example here, the boat travels around a circular path of rho, which is equals to 40 meters at the speed increases with the time with the rate of v equals to 0.0625 t squared. So here, from here, you can see v is a function of t. So if we differentiate v with respect to t directly, so you will have 2 times 0.0625 t. So find the magnitudes of the boat's velocity and the acceleration at the instant when t is equals to 10 seconds. So the boat starts from rest, so you have to assume that at that position, that is the origin, so the v is equals to 0 and the time is equals to 0 at that point, at that instant. First, calculate the velocity at t equals to 10 seconds. And then calculate the tangential and the normal components of acceleration and then the magnitude of acceleration vector. So the velocity vector, so that is your velocity vector. So at time equals to 10 seconds. So V, substitute time equals to 10 seconds. So you have 10 to the power of 2. So that will give you the V 6.25 meter per second. So remember, we have to find the V as well as the V dot. Okay, so you have this. Okay, so the acceleration vector. So always represents it in the form of vector first. So you have the acceleration is equal to AT UT plus AN UN. Now AT is actually equals to V dot. So UT plus V squared over rho. So V dot, then you have to differentiate your V with respect to time. So V squared for the V that we have here, we have already found the V is equals to 6.25. So that is your solution here. Okay, so when you differentiate, okay, that equation, you got 0.125 t. So just substitute t, which is equal to 10 seconds to it. So you have the acceleration of 1.25 meter per second square. So remember, you have to find the v dot. Okay, you have to know the v. Then only we can write down the acceleration vector and the magnitude. Remember that. Okay, so that is the normal acceleration. So v squared over rho is always the normal acceleration or the centripetal acceleration. So then the magnitude, you can take the magnitude by taking the square root of AT squared plus AN squared again. So we got 1.59 meter per second squared. So another problem here. So we have the train engine at E has a speed of 20 meter per second and an acceleration of 14 meter per second squared. So you can see the angle given that is 75 degrees. So if we were to resolve it to the normal component, so that will be 14 sine 75 degree. And then we have the v, that is the tangential velocity of 20 meter per second. So what we can do now, find the rate of increase in the train speed at the radius of curvature of rho of the path. So first, you have to find the tangential and the normal components of the acceleration. Then calculate the v dot and calculate the radius of curvature. So the radius of curvature in this case is not given. So therefore, that is why you have to calculate. So first, going the accelerations. So you have the tangential component. Okay, so AT is actually 14 cos 75, AN is AT. So sorry, the 14 sine 75. So we got your AT and AN. So the tangential component of acceleration is the rate of increase of the train speed. So AT is actually 3.62 meter per second square here. So and then the normal component is given by the V is given it's given as 20 meter per second. So you take V square, okay, and then we have already found the AN earlier. So from here you can find out the radius of curvature. Okay, that's all for this section. Thank you very much.